In part 2 we look at the interactions in more detail, and we look at amplifiers as multiple stages. The big question is mu0 really constant? Mu0 is basically used as the constant in the derivation of the equation. And you can have a look at the operating line of an amplifier, and it presents the relation between the input voltage and the output voltage of a circuit. The input voltage is presented on the horizontal axis, and the vertical axis presents the output voltage. It's basically same as x and y graphs that you probably learned in high school. The slope of the operating line is logically amplification. And the ideal case, the operating line would be a straight line. Never the case. This is a graphical representation. The yellow line is the operating line. The horizontal line represents the input voltage. The vertical line, the output voltage. And if I have a sinusoidal input voltage, that via the operating line generates the green output voltage. And if the system would be perfectly linear, well, I would get the red output voltage. So the difference between green and red is a distortion introduced by this nonlinear line. So we can conclude that distortion is caused by a nonlinear operating line. And therefore we will introduce the local amplification as a tangent at the operating line. And this is an example. This line is the actual operating line, and at 2 points I've calculated the tangent, and this is at the zero crossing, and this is at a negative voltage. And you can see that the amplification at the zero is 197, and here it has been reduced to 118. So with a nonlinear operating line, the local amplification varies along the position of the operating line. And again, no operating line is perfectly straight. And although the operating line does not look very nonlinear, the local amplification varies from 197 at the zero crossing to only 118 at the negative input voltage. That's only 60% of 197. So we end up with an interesting contradiction. When mu0 would be a constant, the amplifier would not distort, so there was no need to apply feedback to suppress the distortion. When an amplifier distorts, and I don't know one which doesn't, mu0 cannot be a constant. And that takes the foundation of the nice equations away. And this relates to the interactions mentioned earlier. It's funny. We derive an equation in which mu0 is a constant for the reduction of the distortion, which is caused by mu0 not being a constant. That's funny. Mathematically, this is cursing in church. That's a Dutch expression, but I think it will make perfectly clear what I mean. It's nonsense. Well, now if you look at a composite input signal, let's say a strong low frequency tone and a weak higher frequency tone, the amplification of the higher frequency tone depends on the actual value of the low frequency tone. And this results in a modulation of the higher frequency tone. This is the input signal, this is the low frequency, this is the high frequency, and they both have a constant frequency and a constant amplitude. And this is the output for the higher frequency. I've subtracted the low frequency component, and you can see that the high frequency is modulated in the positive parts of the low frequency cycle is stronger, and at the negative side it's less. And if you look closely, you also see the double frequency of the lower frequency. So apart from intermodulation, you also will have the harmonic distortion. And the amplitude modulation is caused by the variable local amplification, and the clear second harmonic can be concerned as well. So one important conclusion is that the local amplification is essential. So the best one can get is that you get approximation equations. And it's obvious, you don't have to be named Einstein, to see that the less well the approximation is, read the less straight the operating line, the less well the calculations will approximate reality. and the more important the interactions become. What are further consequences? Well, due to the nonlinearity, the operating points of the individual amplifications shift. The operating point is the setting in voltage and current of a transistor when no signal is applied. And when the signal comes in, the current through the transistor is varied or modulated. And if all was well, this would be perfectly symmetric around the operating point, but due to the distortion, asymmetry is created, causing the operating point to shift. And I'll illustrate that with a 6-cycle tone burst, using an input signal to this amplification stage. The upper trace is the output signal, the lower trace is the average value of the collector voltage, which is actually operating point. And for the sake of clarity, I've shifted the two from each other away so you can see the curves more clearly. But it's not caused by the effect, it's just me that did it. So we have the distorted tone burst. This is the operating point when no signal is applied. Basically these are the same. Yeah. If I look at the average value of the distorted tone burst, I see this step change, which means that when this tone burst is coming through, I also get its envelope for free. And when the whole amplifier is DC coupled, this lower trace signal will also show up at the output. And virtually all semiconductor amplifiers nowadays are DC coupled. And it manifests itself as an, of course, unwanted artifact. The shift rapidly increases with the modulation depth of the amplifier stage. This is illustrated here. This is the input voltage, and this is the deviation. And you see it starts to shift far more rapidly than proportional here. It's a close to quadratic relationship. And this kind of effect, there'll be another one, I'll come a bit later, which causes the desire for headroom, because the artifacts rise stronger than the music signal. It's a bit weird that you should need the headroom for an amplifier, because if the amplifier would behave the same up to its clipping limit, you should not be able to notice whether you're at 10% or at 99.9% of its operating range. So when you start to have desire for the headroom, you probably have artifacts generated which become stronger, more stronger rapidly than the input signal. We'll come back to that later. But mu is also frequency dependent. Why? Well, in order to maintain stability of the amplifier when feedback is applied, the open loop gain must decrease with increasing frequency above a certain cover frequency. In the ideal case, the decrease is realized at a 6 dB per octave first order low-pass filter characteristic. The closed loop bandwidth cannot be taken too high because of sensitivity for HF signals. When your amplifier could go up to 2 MHz, for example, then you better use it as a medium wave transmitter than as an audio amplifier, because you don't want all these high frequency stuff being processed by your amplifier. But your open loop amplifications start to drop above the closed loop bandwidth, divided by mu0 beta. So, in a simple equation, let's assume that the closed loop bandwidth is F max, and the frequency from which the open loop amplification starts to drop is F max divided by mu0 beta. With a high value of it, this frequency will end up in the audio band. Let's say if F max is, I'll come back to it. So one must choose between two kinds of misery. Either use a low value of mu beta, which is constant in the audio range, or a high value of mu beta, which will start to drop in the audio band. This is illustrated here. This is the closed loop amplification, and we have taken for the example 200 kilohertz, and the reference value is 0 dB. Now, if I use a feedback factor of 10, that's 20 dB, I can get this curve for the open loop gain, and it starts to decrease at 20 kilohertz. I could also use 40 dB at low frequency, And then an open loop amplification will look like this, have a feedback factor of 100, but the decrease starts at 2 kHz. So, some people say, very clever, well, I can apply a higher feedback factor, so apply a higher order low pass filter to mu. And using a second order low pass filter, the feedback factor could be increased to 100 and it could still maintain a constant feedback value in the audio band and the closed loop bandwidth of 200 kHz. So that's trying to save everybody. But what about the law of conservation of misery? Well, the amplifier will be less stable with complex loads, but it will also manifest itself in a temporal response. And well, this is an example. I've drawn here the characteristic up to 100 kHz, and within 0 to 20 kHz the deviation of the response is plus or minus 0.042 decibels. Nothing to worry about. That's virtually identical when you have a first order system with a color frequency of 200 kHz. So that looks very interesting, but now look at the temporal response. If we put in a Dirac pulse, then this is the output of the amplifier. And it gives a time smear which spreads over at least 50 microseconds. Whereas the temporal resolution of human hearing is about 5 microseconds. If I use a first order filter, the impulse response would look like something like this, which is about 5 microseconds, which is in the same order of magnitude as the temporal resolution of human hearing. So, the higher feedback factor, as a lower distortion figure, can be accompanied by a lower temporal resolution. And time smear manifests itself as a loss of detail. A slope of 60 beat per octave gives the least time smear, and note that up to 100 kHz, no differences worth noting are measurable in the frequency response characteristic. But there are audible differences. So the importance of the response from 20 Hz to 20 kHz is only very relative, which is consistent with something we've seen before. Now, look at the interaction between the distortion and the bandwidth limitation. The open loop bandwidth limitation can be obtained by a simple first order filter, think of a resistor capacitor combination. But the average charge on this capacitor can change due to the nonlinearity of the amplification stages, or what we call local detection, and create in that way a memory for the envelope of the input signal, which subsequently shows up at the output. Again, it's the same figure again. So we have this 6-cycle tone burst, and then we have this envelope of it, and now we apply the filtering, and note that the envelope is made of lower frequencies than the signal generated, whereas harmonic distortion only generates higher frequencies. So this filter obviously filters the signal, and the envelope is of lower frequencies, so the influence on the filter is higher on the envelope than on the actual signal. And how much, of course, depends on the filter color frequency, but in general, the ratio between the signal and its envelope will deteriorate. And when the upper loop gain starts to drop in the audio band, this could be very disadvantageous. You can see it here. This is again the upper half, the same as before, but now we have the filtered output. So this is the filtered output plus the envelope. And you see it is actually no longer an AC signal. It has a very strong DC component, which is in the same order of magnitude as the AC component from the tone burst. Because the AC signal gets reduced more by the filter than the low frequency envelope. And these kind of artifacts can lead to unrest in the audio image, but it can be improved by keeping the open loop gain constant in the entire audio band. And this will keep the ratio between the signal and envelope constant. And as a bonus, it will also lead to a shorter recovery time after overload. This is an example. Now we've shifted the color frequency to above the limit of the audio band, and you see that the changes are very minor. If you look very closely, you can see a sharp edge here and a little less sharp edge here. That's due to filtering. But say in general, the thing looks a lot better and far less affected by the filtering. Now, most amplifiers use several amplification stages, each of which has its own distortion, but in only general and a single overall distortion figure is used. And the suppression rate by feedback depends on the position of the stage within the amplifier. And for those who don't believe me, you can find the whole derivation of this at our website. And it boils down to the further you are away from the output, the less the suppression is. And when you come to the entrance, the differential stage, where input signal and feedback signal are compared, is effectively placed outside the feedback loop. Its distortion is amplified as much as the input signal. So, due to the frequency-dependent feedback factor, the distortion increases with increasing frequency because the differential voltage increases. It's not that hard to understand if you look at the simple equations. Then you see that the differential volume, which is input minus feedback signal, is equal to the input signal divided by 1 plus B beta. And this is exactly the same as the actual amplification itself. So from the frequency above which mu starts to decrease, the differential voltages increase at the same amplitude with the input signal. And when it occurs in the audio band, it can have audible consequences. And here we end part 2.